everybody. Welcome to class. Welcome to the what is it? I think the fourth or the third week. What is this? This is the fourth week. Okay, there we go. I think this is the fourth week. So yes, we're getting really close to the ending here. And we actually really are in terms of the content at the very least. So hopefully you all are doing good with your assignment. You had the function assignment due yesterday, I think, and then you have the battle royale assignment due pretty soon. So yes, make sure you guys get them done. So anyways, let's get going to the content. So last time we talked about arrays, and at the end we were just kind of, I was just showing you some random things. And so today I want to show you one more method of storing potentially a list of information, and that is vectors. I want to show you vectors. Along with vectors, we can get the opportunity to talk about range for loops, which is it's a for loop with a little twist to it that is meant to help you in a way to make the code writing easier. And also other languages have a range for loop, so we kind of added it to C++. Not we, but the people that decide C++ added it because everybody was asking for it. And like I use it a lot in Python. A for loop in Python, like a generic for loop in Python, is a range for loop, and so it's a very nice thing to have. So we'll talk about that, and then we will talk about searching and sorting as concepts and how they are applied to arrays and vectors as well. So that's the goal for today. And again, if we don't get through all of this, then we'll get through it later on, since we still have tons of time. Really, after assuming we cover all of these topics today, all we have left is that is structs. So yeah, we'll take our time with them. So let's go ahead and jump into coding. Yes, let's jump into this. Okay, and I call the little file easy vectors just to kind of show that it's easy to do vectors. So I am going to, however, I want to pull up something known as the standard template library in C++. So again, school environment, you guys are learning to program, and so you're not allowed to use a lot of features that would otherwise be available to you. And the biggest one of those is going to be the standard template library. And so I'm going to post a link from the Wikipedia. I'm going to check that out later. And so what is the STL, or standard template library? Let's read the first line from Wikipedia. It's a software library for the C++ programming language that influences many parts of the C++ standard library. It provides 4 components, and those are algorithms, containers, functions, and iterators. So what is it actually? Well, we know that libraries give us additional functionality and save us time by giving us some of the most commonly used math functions, for example, right? We got the CMath library that is giving us like a POW function that we practice a lot, absolute value we used, and those kind of things, right? We also have like kind of like the string library that had all those nice things like finding the length of a string and substrings and so on. We had the stdlib library that allowed us to use rand and randomize pseudo-random stuff that I showed you. We have the time library for getting the time from the machine. There's also some system libraries that allow us to interact with the operating system. For example, stdlib.h has a way to call system commands. So you can send, since from your C++ program, you can send commands, bash commands, to the terminal in Linux, specifically to Linux. But there are equivalents for Windows and Mac, that kind of thing. So like in the Battle Royale assignment, for example, if you wanted to clear the screen and you don't want to use that nasty cout statement in the PDF, you can also use system clear. And that's what I was talking about on Discord with somebody over the weekend. So different libraries allow us to do different things, and that is the whole idea is that not that we can't code that ourselves, but why should we do it when somebody else has done it and they've done a better job at it than we probably could unless we spend a lot of time on it. So ultimately, standard template library is sort of a combination of a lot of other additional functionality. And so I said, as Wikipedia says, there are 4 parts: algorithms, containers, functions, and iterators. So first, let me talk very briefly about algorithms. Algorithms, we know what that is. I defined that early on in the class. And basically, you can think of that as a cooking recipe in this form of like a step-by-step process to get from A to B, and A being what you start with and B what you want to end up with, right? And so there could be an algorithm for searching stuff or sorting stuff. That's kind of what we will get to eventually, but I'll show you how to do those by hand. And but there could be a lot of things. And actually, when you get to CS 302, if you're a computer science major, that is essentially what the whole class is about: data structures and some algorithms. In fact, there's another follow-up class to data structures, which is CS 477, which everyone has to take as a CS major, and that is called analysis of algorithms. So, and it's basically a continuation of the 302 course. In fact, they repeat a lot of the things, but they go into a deeper level. So data structures and algorithms are a big deal in computer science. And so all of this, I guess this is sort of a spoiler, all of the stuff you learn there is contained in that algorithms library, and you would never actually have to code it in real life. But why do you learn it? Well, it's the same reason when you go to a math class and they teach you how to do math like long division, or they teach you how to do fractions, or you know, if you go into more advanced math, like if when you're learning how to do calculus, sometimes they teach you the really long way of how to maximize. Like when you're doing a differentiation, when you're getting the area under the curve, they teach you the long way on how to add all the little pieces together and how you split those pieces into smaller pieces to get the most accurate measurement. And then they just show you how to actually do integration in the easy method. And so why do they do that? Because they want you to learn how it works and sort of the theory, so that you better understand it, so that you can use it on your own purposes, and also to kind of sounds weird, but not necessarily make you smarter, but make you think more logically. They make you think more analytically and things like that. So that's kind of the same reason why we show it, but also because unfortunately there are a lot of people that have a computer science degree or not have a degree, but they claim that they're good programmers, and then they apply for jobs. And when they do apply for jobs, they don't know anything. And so what that has sort of resulted in the programming world is that if you're applying for anywhere decent, they are going to give you a programming test. And that programming test is probably going to involve you coding something, and it's going to be coding a data structure or an algorithm. And there's a very high chance that it's going to be something that you learn in your data structures class. And so it's a very scary thing, to the point that even my doctors ran away, because she was like, oh no, programming test. But ultimately, that's one of the sort of motivations, I suppose, for learning data structures. Although I was surprised to hear somebody who had an interview last, I think it was semester or semester before that the hardest thing that they asked him to code was a linked list, which is something you actually learn in 202. So that was nice. But I have heard other people get shortest path problems, like from Google, for example. Interviews for Google, they ask you that stuff, and that's 302 land. So anyways, algorithms contains basically the solutions to all of these things, so you can very quickly use them. So that's what is in algorithms, and that's also what's in your future if you're a CS major. Functions. What does functions really contain? I mean, it has a bunch of math stuff, as far as I remember using it. Like, there's another way to randomize things using in functions that's better actually than stdlib. But if you're ever curious about what it contains, you can just literally Google the functions library. Let's see what it contains, and I can refresh my mind. Let's see. Oh, this list is really nice. I'll share this. Here's a little list that I just found that contains all the libraries and summaries of things they have. So maybe here we will find function. And if not, then that's still pretty nice. functions. Contains classes and functions used by standard library algorithms. I guess maybe more algorithms. The time that I have seen functions used is when they were randomizing things, creating rand stuff. So yeah. And anyways, so amongst the standard template library, one of the nice things they have are known as vectors, which is what I really want to talk about. And so I'm going to go ahead and share another link that one I have prepared already, which talks a little bit about vectors and kind of what we're going to be doing with them. And more than that, all the different things you can do with vectors. So I want you to think of vectors as an array, but an array like advanced, or not advanced, but what's a good terminology for that? With that, there's a bad comparison that I have in my head that I don't want to say because it's kind of weird. But I really can't think of anything else. So I'll just say it's like an array on crack, basically. Okay, so don't do drugs, kids. But yeah, that's kind of what, you know, if you've ever heard that term, that's what it is. Like, it's a really strong array which has extra features on it. And so one of the biggest limitations on arrays is that when you declare the size of the array, that size is set forever. And so, have you heard people come? Yes, I have. It's a pretty cool website. So, but anyways, so with arrays, the big limitation is you have to define a size. Now, when you get to CS202 and you discover dynamically allocated arrays, that is one way that you can declare arrays of different size at runtime, which means when the program is running. But you're actually still limited to the fact that when they get full, you got to make a brand new array, copy everything over, doing kind of a very quick example I did with deep copy, which they'll go more in detail in 202. But you're still stuck in a situation where you are limited by the size of the array and having to resize. But the thing is, you have to do that by hand. Like, you have to keep track of that. You have to keep track of when the thing gets full to add more space and so on. Oh, this is good. Oh, it was getting in the screensaver. On the other hand, there are such a thing called linked list, which, as I was mentioning, that's one of the things they asked in that one interview. And with linked list, you remove the limitation of having a fixed size. With the linked list, when you learn in 202, you're able to just append things at the end and also remove them very easily. The limitation of a linked list, however, is that you can't access things very quickly, because with an array you have the index. So if you know that you want to get the 5th item in an array, you can just use your square brackets and put a 4 there, right? Because you go from 0. So that what 4th is technically the 5th thing. Boom, you get there extremely fast. With a linked list, you can't do that because for now, even though you've never seen a linked list and this is the first time you heard about it probably, you can think of a linked list as a chain. And so, in fact, think of the word linked in list. So the word link, you know, think of when you're thinking of something linked together, you're thinking of something that's kind of hold together like that. And so, in fact, that might be a good idea to throw this in here. If you think of a linked list, you know, first of all, an array would be something like this, right? You got all your indices. With a linked list, you can think of individual indices per se, which are no longer indices, it's just pieces of your list, and they're sort of chained up together like that. And the reason why it's very easy to add things to your list is because all it is you just create another link per se, and then once you create it, you basically just append it to the end of the list. You could also append it to the beginning of the list. You can even do some fancy stuff and split the list somewhere and then just add it in there, right? But the problem is, typically you only have what we call the head, and sometimes you also have a tail that point to the beginning and the end of that. And those are your only ways into the list. So if I was to try to access this guy, in this case, which is known as a singly linked list, the only way that you can really do that is you have to go through the pointer here and then kind of walk your way all the way and get there. and then you're there. So they kind of upgraded that into a double linked list, which just allows you to go both directions in the arrows. But that still means that, okay, the other way that I could get there would be maybe from the end this way, but that's still a pretty long path. And then you're like, well, why don't I just create some sort of pointer that links to that middle spot? Yeah, okay, but then you have to create one of those for each of the elements of the linked list, because now if I want to access this one over here, then I still got to go either this way or this way, right? And so both are not, you know, the solution is not to add more pointers, because at the end of the day, then this whole list of little pointers here is going to just end up being an array of them. And so, you know, we're just kind of working around the problem without really solving it. However, like anything in the world, there's pros and cons. The pro here being that you can just keep adding to the list and you never run out of space per se. And the con being that you can't access things as quickly as possible. This becomes a common theme when you get to data structures, in the sense that some things are good for some things and not so good for others. There is no fit-all solution to everything, right? Okay. This is linked list. Again, you will really figure out how this is done in Tool 2. And I did kind of lie when I say that you can just add things forever, because there is a limitation, of course, and that is how much space you physically have in your computer, right? If you have a stick of RAM that's only 16 gigs, and you try to insert so many things that you fill that stick of RAM, what's going to happen? You're either going to run out of memory, or you're going to start writing on the hard drive, which is going to make things super excruciatingly slow. And even then, you could run out of hard drive space, and then you really physically run out of memory. So yes, there is a theoretical limit to that. But what I'm saying is, it's flexible. You can add things, you can remove things. There's no need to resize. Whereas if this guy is full, and you want to add one more thing, then you got to make a brand new copy of it, copy everything over, and of course the brand new copy being a little bit bigger, so you can add that extra thing. And yet again, you're still going to end up reaching to the point where it gets full again. And if you want to put something in the middle, yet again, you got to make a brand new copy of everything, so that you can shift everything by one and then insert something in the middle, right? So there's pros and cons. And not just that, but doing all these physical, not physical, but these virtual manipulations of these things, such as, like, for example, inserting something in the middle there, or copying things over, is code. You got to code all these things, and they're prone to potential issues, right? But it's not as hard as you think. That's why it's something that's taught in Tool 2. It's not that hard. I mean, you guys are very close to hitting Tool 2 world now. So the thing is, though, even though it's not that bad, nobody wants to code this every single time they're working on a project, right? They want to just use a library that does this. And so this is how vectors are kind of born into play. Vectors, it is my understanding that vectors are arrays. They are not linked list. They are dynamically allocated, which means that they are storing what is known as a heap. Again, don't worry too much about that. Tool 2 world. But they have the ability to add things in the middle or in the end and never have to worry about resizing. Now, that's because, yes, you're still running into the problem here with the top one. However, that is all handled internally, and you don't really see that. It is all handled behind the scenes. All you gotta interact with the thing is to insert things or remove things. And you don't have to worry about how the things are resized, how they're copied, and you know, there's a decopy so that we can throw more things in there. Or if I remove something, how do I have to like shrink it again? Because that's the other thing, right? If I was to remove in this example, this one now, if I want to remove that middle one there, then now I got a broken link and I gotta reconnect them, which is not too bad here. Just go ahead and do that. The hard part is actually getting there. With the top one here, if I want to remove something, I gotta shift everything down unless I keep track that that's empty, which I can, but it's work. With vectors, that's all taken care of. You just enjoy them basically, and all the hard work is done behind the scenes. And so that's good. This will be both a good example of how powerful using other people's work is, just in this case, you know, standard template library. So a good example of that, and also kind of give you power so that you can do your own little programs and not have to worry too much about this memory management stuff. So the first thing you should know is how to actually start using vectors. And so you have to include here one of the standard template libraries, which is going to be, surprise, surprise, vector. These are called vectors, okay? And I'm gonna copy and paste the definition. Well, I don't think I can copy between the VMs. Sometimes I can, but sometimes I can't. It's kind of like, is it in the happy day or a angry day? Let's see what it is today, and it is angry day. Okay. So probably have to just restart the VM. Okay, so I'm gonna copy the definition from the link that I posted. Vectors are sequence containers representing arrays that can change in size. And yeah, so arrays that can be changed per se, okay? And then you can read the rest of the definition from the link, which, yeah, I did post. So, okay. Oh, good point. Thank you for that. There we go. So, yes. Vectors are sequence containers representing arrays that can change in size. Thank you for letting me know. Okay? And so, you can see there that there's a lot of functions that at the bottom. If you look at the bottom, it says member functions. We still don't know what classes are because we haven't talked about them. But all those functions are sort of abilities that you can use. If you think of the string class, when you were using strings, I don't want to use the word class because I haven't really talked about it, but you know how you had the find or the substring or the length or size? Those are functionalities that has. This actually has a size as well that you can use, just like strings. But there's even more things that you can do. And it gets really complicated very quickly if you want to go deep into it. But if you just want to use it at a sort of superficial level, like I want to add things to this list and remove things and maybe insert in the middle and so on, then that's okay too. So, yes. Is it really blurry? I can make it a little bit bigger. You guys let me know if it's still blurry. Or try to refresh. Not blurry. I'll still zoom in a little bit. I can probably zoom in a little bit to help out. But you should make sure that you increase your increase to HD if you are watching, and it's that'll help the resolution. You know, assuming that you have the internet for it. But yes, okay. So we also want to make sure that we actually include our IO stream, since we are going to be using some C in and Couts for this example. And then just to not have to write using namespace, well, not so that we don't have to write std cout every single time. For the sake of speed, we're going to put, of course, we're using namespace std. There we go. Hard to talk and write at the same time sometimes. We can start out by preparing a hello world program per se. Okay, and then let's just make sure that we're in the right spot. There we go. Okay, we're fine. Cool. And so, all right. So how to use these vectors? The first thing we want to do is how do we declare one of them, right? Because you know you have to declare anything you're using. So if you're declaring an array, you know how to do that. Declare a variable, you know how to do that. Declaring a vector is not that complicated, but the syntax is a little bit weird because of how they actually work. And of course, you know, think back when we started the class and how everything was weird in the sense that we were all just kind of like, yeah, just magic. Just accept that this is how it works in magic. And now we pretty much know everything here, what it does, right? We got into that point. But the one thing that we really don't know yet, how it truly works, or why the syntax is like this, is static casting, if you use this method, right? You remember static cast, you know, if we have something like double T, and then we are casting that T into an integer, something like this, and let's say this has a 3.5, and we run this, it's going to print out a 3, right? Or negative 3. Did I have to put a negative? Oh, yeah. I accidentally put a negative there. That was weird. But yeah, I guess we'll leave it with you. But anyways, so if you remember this syntax, this is kind of weird. And I don't know if you remember, but if you don't, that's fine. I said that the reason the syntax is weird is because it's kind of like how templates work, which is a tool 2 subject, which, again, you have to wait until then. Well, this sort of same syntax is how vectors are going to be created. So that's why I kind of threw that. So let me just comment that out. The way you create a vector is you actually write the word vector. And then in here, oh, you can also use the visual code to tell you these things. So that's kind of nice. The next thing you want to do is you want to put the data type that you want to store. So you are still limited with vectors to have to be, again, homogeneous, which means the same data type throughout. And so we're still, we're still not in that ideal like in Python where you can just store any data type that you want. You still got to make an array of integers, an array of floats, an array of something, one data type. You can't just throw them all in together like a bunch of stuff, which you can do in some languages like Python. In Python, I can have a list, which is, you can think of it as kind of like an array, but it can be made up of multiple different data types. You can have an integer followed by a float, followed by another integer, followed by a double, followed by a string, followed by a custom data type, and so on. You can even have arrays inside of arrays. So, you have a little tiny array in there as well. Right now, even though vectors are super cool, we are limited in that. There are ways around that when you get to learn about pointers that you shouldn't really do in the first place, but you can work around that. There are other ways you can solve these kind of problems. But anyways, so in this case, let's say we want to make an integer vector. Again, I don't want to say the word array anymore. I'm going to use vector, and then just give it a name. So we're going to call it my vector, just because it sounds cool. There you go. That's your declaration. There's a lot of talking for essentially 3 words. And so if you notice, the reason I have the static cast is because you can kind of notice how it's very similar in syntax, right? You have the less than and greater than signs and the data type in here, except instead of using vector, we're using static cast, okay? So again, if you're curious as to why this works the way it does, I can probably get the template C++ Geeks for Geeks article, and you can read that on your own time, or you can just wait until you take 202. So you can check that out on your own time and how it runs. So yes, although I mean, summer 3 I am doing 202, so I will have all these videos, so you can always come back and check out the video for name templates if you're curious about that. So anyways, that is how you declare a array, a vector, okay? Now, how do we actually insert things into it? Also, notice that there's no size. That's okay. That's handled internally. All you gotta do is throw things in and it'll work. You don't have to worry anymore about size. This is like you pass that management down. You know what they say when you own a business and things like that. They tell you don't take all the responsibility, right? Give it out to other people so that you can focus on the main objectives, right? Similar thing with programming. Don't take the responsibility of handling all these internal things. Trust that other people can do it. So vectors, you trust that they can do it. So we still got to figure out though, how do we actually insert into our vector and remove things, right? How do we handle that? Well, it's not that hard. But to do that, we need to learn a couple of functions. And the first one that we want to learn is insert. So a good insert function for vectors is pushback. So the way you use it is kind of like the way you use the find or the size. You put the name of the vector, the identifier name, the variable name, my vector. Then you put what's known as the member access operator, which is the dot, which we have seen before, but not really talked about it. It will make more sense when we talk about structs tomorrow or the day after. And then what that basically does is it allows you to use any functions that belong to the vector class. Again, class being one of those words we haven't really talked about. But anyways, I guess for now, just trust that putting the little dot, and then just a period, after the name of the variable gives you access to all the functionalities that vectors have. In fact, if I put it here, you can see the autocomplete gives me a list of them right here. So, and if you're ever curious, you can of course use your down arrow and up arrow keys to see what each one does. So actually, we could actually kind of look at them very briefly. So let's kind of look at the, we can see erase. So erase is nice. It actually allows you to erase a specific element. The parameters for that is basically the index of the element that we're trying to remove, which means the position, as you can see there. And it tells us what it returns and so on. Front gets us the first thing at the beginning, which of course you can still, by the way, you can still use your square brackets as with arrays to get the indices of each thing. I'll show you that in a second, but you can also use these functions as well. Insert You can kind of guess what that does. Although, it's a little bit more, it has more power than just your basic insert, because you got to figure out where to insert to, right? And so you can kind of see that this can get pretty complicated very quickly. So we'll kind of skip that for now. The ones we really want to find out are these two, push and pop. Push and pop are very popular names for functions that come from the concept of stacks, which again is 202 subject, but a stack is a data structure actually. One of the most basic ones and one of the most important ones, I suppose, when you're talking about computers, because that's kind of how your memory works. Stacks in 10 seconds, what I can tell you is it's a way of storing things. A stack, you can think of it as a little list of things. Actually, first, let's talk about a queue. A queue, you definitely know, because a queue is kind of like the British term of waiting in line. When you go to the supermarket, pre-COVID-19, I suppose, when there's actually a line to pay for something, the first person that gets in the line is the first person that gets served, right? The first person who pays. And then the person who gets, like, if I get there and there's 3 people ahead of me, those people will go first because we have order, right? That's a queue. A stack works similar but different in the sense that you can think of is in the supermarket, where if you were to keep, like, if you want to go to an aisle where they have like what have I seen sort of, I mean, I used to say the example was milk, but not anymore, because milk, they throw it in from the back. But suppose you go to like maybe like the canned product aisle. Okay, in the canned product aisle, it's kind of like that, and so gravity is supposed to feed the items, and there are little rails. Okay, and so you put a can and you push it back and you put another one. This is what the employee is doing, right? So when you take one out, the next one slides forward, and so they're always sort of at the customer. Okay, think about the can that's all the way in the back. Somebody put that can there, and then they put cans in front, and they kept getting pushed to the back. And so the customer comes and grabs the one in the front, and the back one slides closer, right? But before he gets to the front, suppose it replenishes the shop and then gets pushed back again. That can could stay there for years, potentially. So that's basically how a stack works. In a stack, you insert things into your stack, which we call, you push them into the stack. And then when you take something out, when the customer takes something, you pop something from the stack. But with a stack, the last thing that you put in is the first thing that comes out. And potentially that one item that was put in the beginning is the last thing that's ever going to come out, if it ever comes out, right? Somebody 20 years from now, suppose that they forget to replenish that item. Finally, it runs out to the point where like the last item is at the front, and that one customer buys it, and it would expire like 10 years ago. Potentially could happen, right? Although that's sort of one of the issues of using a stack. That's why with milk nowadays they have doors behind you that you can put it in. And yes, one of the sort of acronyms to remember that are the ones that you put there, which are stacks are last in, first out, and queues are first in, first out, which is like first come, first serve. You can think of that as a more jargon term in our English language. First come, first serve is first in, first out with a queue. And stack being kind of flipped around, as in the last thing that was put in is the first thing that's going to come out. So anyways, that's all I'll say about stacks and queues as an introduction into that. But in a way, that's where the name push and pop come from. Pushing something into your queue, or sorry, into your stack, and popping it. With queues, you use more of the NQ, which is to insert, and then DQ, which is the one that kind of gets served next. But you can also use, I suppose, push and pop in a way. Is pushing the only way to add something to the stack, or does the insert in place somewhere other than the front? Well, okay, if you're a purist per se, then yes, you can only push things into your stack and pop them out in the right way. Of course, you as a programmer have the powers to do anything you want, so you could just kind of cheat and just part the waters and put something in the middle, right? But if you're doing a proper stack and you're sticking to the original system, then yes, that would be the only way that you control. So you'll notice something with data structures in general and algorithms. You control how data is put into your algorithm and taken out. And you do that so that the algorithm can work correctly. And so, you know, a queue works great when people don't cut the line, right? But if somebody cuts the line, then the thing breaks because now somebody's getting served beforehand. But that may be something that you may want. An example of that is scheduling. With scheduling, you have a priority queue. So what that means is that your computer has one processor most of the time. And that processor can only handle one single program at a time. But I don't know about you, but I have like 20 programs running right now. Plus there's probably 100 more in the back end just to have the computer up and running. If your computer can only handle one at a time, how do we actually get this whole multi-programming experience? Well, it turns out that it's kind of like how moving pictures work. With moving picture, in the movie, you have 30 frames a second or 24 frames a second, 60 if you're watching TV. And so essentially, it's just a picture, but it's moving fast enough that it looks like it's fluid, right? Similar thing with a computer. Your computer may only be handling a single program at a time, but it only handles that update for a very small fraction of a second. And then it moves on to the next program that it's working on. And then that program gets another fraction of a second. And it you can think of it like refreshing its image for that part of the program. And so on. And so it does this so quickly that even though it's working one at a time, because it's working in all of them one after the other in an orderly fashion, then everything looks like it's all running at the same time. Suppose that you got this really aggressive program that just wanted to hog the CPU to just run its own computations and nobody else. Then all the other programs would freeze, or they would look like they froze, because this one's just really hogging everything. And I mean, that can actually potentially happen. But yes, so if you want to intentionally have that be the case so that that program wants to finish first, you can do that by increasing its priority. So there are situations where you want to be able to sort of, like Chrome will do that for you. But there are situations where that may be something useful to you, but you as a developer have control of what you want to do with your data structure or algorithm. And so a normal queue, no way to cut the line. But if you want to have that ability for a VIP, then you can do it. Same with the stack. A stack, you shouldn't be able to just put things in the middle. But it's a free country, right? Free world, I suppose. Is it really though? But suppose that it is, then you can do whatever you want. So yes. Anyways, that's getting a little bit off topic though. Really, stacks and queues are actually the last thing that we cover in 202. So I don't want to scare you guys by talking to you too much about stuff that's not even going to be on the test. So anyways, that's where the term push and pop come in here. And they will kind of work here in the same way that they would sort of work in a queue, which is push back is going to push it at the end of the line. And then, actually no, this will work like a stack. Yeah, sorry, not a queue. It's like a stack because push will put it at the end of the line, but then pop will pop that last item. So this will actually work just like a stack. Yes, not a queue. Because for a queue, you'd have to remove the front. I'm sure there's a way to remove the front. So anyways, okay, so you put in our pushback, now what? Now, it's as easy as putting in some parameters here, and that is basically what you want to push into your queue, or vector actually, not queue. So, what do we want to push? Well, we could push a literal, we could push another variable, so let's just do both. Let's first do one with a variable. So, let's make a variable called temp, and let's put 20 in there. And hope you don't hear my puppy crying. Just do that. Okay, let's copy and paste it and let's put something else. This time let's put a literal. So that means putting an actual number in there like that. Okay. Now let's go ahead and try doing it with a little loop. I is less than maybe 3. Maybe 6, a little more. I plus plus. And now let's go ahead and push back I. So we'll put a little count in there. And that's it. Let's just let it be like that for now, okay? So, how do we actually print out what's in there, okay? Let's do it the old way first. Let's do it how we were learning how to do arrays. So with a little for loop. Similar to the one we have above actually. So here I'll just copy paste. However, we don't want to use 6 in there. We don't want to hard code it. So here's the thing. With arrays, we had to keep track of the size ourselves. Like we had to have that sort of management, right? But like I said, in the business world, we want to delegate, right? So we want to give away as much of the work to others. And with vectors, we have to the point that we don't need to keep track of the size because my vector, similar to how strings work, has a size already to it. And so you just call that function, and that takes care of telling you what the size of the actual vector is. Although if I do it this way, I think it's going to update every time, and we're going to have issues printing everything. Yeah. But if we do, then that's okay, because we'll get to see that issue. We may need to copy that somewhere else first before we start actually... Oh, no, we won't have that problem right now, because all I'm going to do is going to print it. But if I was to remove things as I printed them, then this would be an issue. So we'll come back to what I was thinking. Don't worry about what I was thinking there for a second. Okay, so yeah, if you want to do this the old way, then you just use your square brackets and you put your I in there and you're good to go. Let me put a C out in front of that actually. Case in point. Okay, you guys ready for your first ever vector? Bam. Can you see it? Because I can't. I gotta move this a little bit. Okay, there you go. So let's see if what we got is right. Maybe I can put this on the side here like this. So the first thing we put in there was a 20, and then we put a 5, and then we had our count from 0 to 5, which, yeah, there we go, and it's 6 of items there, yeah, so it worked. Perfect. And that's, of course, sort of the old way that you learn how to do arrays. And that's fine, you can use it as much as you want like that, okay? All right, let's go ahead and try to remove something from this. So maybe before we print it out, let's just call the remove. So just remove the last item we inserted. We'll start with that. So we're going to use that pop function that you saw there. So there's pushback. I think the reason they put it at the top here at the ID is because we just used it recently. It might be possible because of that. So yeah. But anyways, pop back. This one doesn't require any parameters. As you can see when I autocomplete, you can see here that there's no parameters. So then where is that going? Note that no data is returned, and if the last element's data is needed, it should be retrieved before popback is called. So be careful about that. All this is really doing is removing that element. You're not getting it back. This is a little bit different than your standard pop function in a stack. If you know, if you ever actually have messed with a stack. And normally with a stack, when you pop something, you actually get that item back. It's kind of like removing it from here. It's more like it just pops into the void and just disappears. So really, here we're just deleting it. We're not actually getting it back. So just FYI. As you can see, that removed the last item. So the vectors print the exact same way as the arrays? Yes. Yes. But here's the bonus. You don't have to worry about its size at all. You can just stick to basically inserting as much as you want and never ever have to worry. So like think back at I don't know if you had any assignments like this, but where you have to declare the size of the array, so you have to figure out how big it is ahead of time. Here you don't. You just worry, let the computer worry about it, and you're good to go. And if you ever want to figure out the size, you can just call size instead of keeping track of that by hand, manually. Like actually keeping a variable, increasing that and decreasing it as things move through this thing. So yes, it's very, very useful. And you can still use your old array syntax that you learned last week. Except you can also do other cool things. So this is kind of as much as I want to show you, but I do want to show you the range for loop and other things. But here, let's try to do something here, what I was going to show you earlier. So I want to show you what happens if we try to do this. I think we're going to run into some problems. And I hope we do. Not pushback, sorry, pop. So here's what I'm thinking is going to happen here. Actually, let me run it first. Yes, perfect. Okay, so that's what I thought would happen. Okay, but now that I confirmed it, I can tell you about it. Okay. So this is a potential issue that you might run into if you're not careful about this, okay? So the way I have this set up with this range for loop is that, or not a normal for loop actually, is I'm running from I0 to the size of this. And then I'm printing it and then deleting it. So in my head, when I was coding this, I would have been like, oh, okay, I'm gonna print everything in the vector, and as I print it out, I'm gonna delete it out of the vector. That's what I was thinking in my head. But as you can see, that's not what I got when I ran the program. I got a 20, I got a 5, I got a 0, I got a 1. So I got the first 4 things, and I lost the last 3. Actually, I lost the last 4 because I actually commented out to the remove. So there should be a 5 at the bottom here, actually. So I lost the last 4. So I got the first 4 and I lost the last 4. Why? Okay. Actually, here, before I answer it, I ask you guys, why? Why do you think this happened? If size is supposed to return me the size of the vector, this should have run potentially 8 times. Is it because it prints from top but pushes from bottom? No, there's more to it than that. Try again. And this, by the way, is not something strictly limited to vectors. This could happen with anything. Is it because it pops from top? No, there's more. It has to do, I guess I'll give you guys a hint. It has to do with the size and the way the size function works. So I'll let it simmer for maybe a couple of seconds, unless anybody wants to guess, while I drink some scrumptiously tasty water from the Nestle brand. Is scrumptious a word? Where did I hear that? There's a movie I heard scrumptious from. Maybe Pulp Fiction, maybe? I don't know. As you remove, the size decreases. Very good. Yep, you got it. That is exactly why. So here's what happens. Remember in for loops, this is your initialization expression, the int I equals 0. And this is the actual logical expression that gets run every single time you iterate. So you go to the top of the loop. And then at the end, of course, of the loop, you get the update expression here. I don't like that I put a space there. That actually bothered me. I didn't notice that until now. But yeah, so yes, that is how a loop works. But here's the thing. Every time that you're calling, that the loop ends and you go back to the top, so you run your update expression and then you check your logical expression, it's calling size again. So it's getting you the latest size of the array. So the first time it runs, it gets the correct size per se, in the terms that it gets a size 8. Okay? However, when you do the pop at the bottom, the size decreases to 7. And so the next time that you come around, size is 7. And then 6. And then 5. But as this is happening, I is also increasing. So you started at 0 and 8. Then you went to 0 and 7. Or sorry, 1 and 7. Then 2 and 6. 5 and 4. And then finally you get to 5, 4 over here. And so at that point, the loop actually stops. So even though this thing only got halfway there, then actually I went to 5, but you should have gone to 4. But yeah, so you start at 0, and I guess you're looking at it. So I guess it makes more sense if I do my hands this way because it's mirrored. So you start out with 0 here, and you start out with 8 here. The next time around, this goes to 1, and this goes to 7. 2, 6, 3, 5. That's still okay. But then you get a 4, 4. There we go, yeah. And then that is equal. So that means that 4 is no longer less than 4. And therefore, the whole thing terminates. Wait, where did the size 8 come from? Okay, so the myVectorSize gives you the current size of the vector. That's an internal function, and it works the same way. You can, if you remember how string size works, it's just a function that is internally kept, so you can very easily access it. And so we pushed 8 things. We pushed 2 of them this way here, and then we pushed 6 of them this way. So we have 8 things total. So size should return 8. And if you wanna confirm that, you can of course print it out here. And just put 2 on lines. That way we don't get it mixed with the list of numbers. 8. There you go. Okay, cool. All right, that's fine. So yeah. Any other questions? No. Okay, good. Yeah. So basically, that is what's happening. So as I is increasing, size is also decreasing at the same rate, and so they meet at 4, 4, and that's why the thing stops. So what is essentially happening can happen not just for vectors, but basically anything you keep track of. Remember that any functions that you do will recall themselves. Will be called again when you get to the logical expression here. So anything that you have in here is going to be computed every time that the logical expression runs, which is every time that the thing loops. And so this function size is going to be potentially called every single time. And because you're popping, every time you pop, internally it keeps track of that, and it keeps track of the size, so the size is going to go down every time you pop, right? And so that is why this is breaking. The solution, of course, is we want size to remain the same when the for loop starts, right? And so the way we can do that is we can create a temporary variable, call it s for size, and then just save the size there. So I'll just go ahead and get it from there. Okay, and the reason I'm doing this is because this actually kind of premises really well into a range for loop, so that actually kind of worked out. So talk about segues. Bam, that fixes our problem, because now this logical expression is still being run every single time this runs. Here we go, I'm not pointing at it. There we go, now I'm pointing at it. This logical expression runs every time. However, the s is always going to be 8. So now this is working correctly, because even though the size will decrease, that's okay, because we saved the original size so that this can loop the right amount of times. So it's a little bit tricky. You gotta kind of, it's not gonna maybe make sense until you actually try it out and you run into this problem. But it's a very, very common thing to have whenever you're calling a function that computes the size of something, because the size is changing every time that you remove things. Now, this wasn't a problem before when we were just printing, because the size was always the same. It's only a problem if we try to delete after we print. So we're basically modifying the vector between each iteration of the loop. Okay, so now we know how to insert and how to delete. I think we'll stop at that for now. And as I said, I'm going to segue into what is another way that we can, because I mean, I don't know about you, but I don't like this whole idea of creating some temporary variable because of this. I feel like that is more of a limitation in what we can achieve as developers, right? And so the solution to that is going to be the range-based for loop. So I don't think I have posted this link, so let me go ahead and post it. And so that is the documentation on that. And so what is a range-based for loop? If you look at the top of that, there is a line that says for range declaration, range expression, and loop statements. Apparently until C++ 20. So, oh, so that's changing. That's interesting. Oh, so they're adding it. Oh, that's pretty cool. So, as I was telling you guys the other day, when I showed you what the different C++ versions are, C++ 20 is supposed to be coming out, I suppose, this year. So, in fact, I don't know if the documentation is already, like if the ISO thing is decided and they're just implementing it now. But C++ 20 will have some changes and additional features. And one of the things they're actually changing is the range for loop that I'm about to show you. So, I suppose that it'll still work the same way that I show you, but they're going to add some extra features to it. So that's kind of cool. I'll definitely keep track of that. And, you know, once they actually have a working compiler for that, then I can show it. I can make a video someday. But anyways, so okay, range-based for loop. Let me just go ahead and actually write one, and then I can sort of talk about it. How do I want to do this? Let me just, I want to show you autos, because autos are pretty cool, but for now, let me just go ahead and do the most basic one that's going to be that'll make the most sense. So we're going to call this, I want to use I, so let's just use the letter K, why not? Int K, and then my vector. Let's just do this. Yeah. I think this will be a good start for this, so I don't confuse you. Before, let me make sure this runs. It has been a while. Range for loop only available. Oh, yeah, okay. So because range-based for loop is actually a newer thing from 2011 C++, you actually have to do the little flag here. I'm surprised that's a warning and not an actual error. I guess maybe it added it for me manually. But yeah, okay. So compile that, and then running it to make sure it works. Did it do anything? Oh, well, duh. I deleted the whole thing in here. I deleted the entire vector after doing this. So let me go ahead and comment out the deletion part so that I can still have my vector alive and well. Yes. Okay, cool. So as you can see, this is the old one, by the way, and this is the new one. As you can see, both are the same. So, okay, now that I know that it's all working and everything, let me go ahead and show you. So let me scroll down here so you can see it and talk to you. If you don't put the condition I is less than string size, would there be an error? If you're talking about, per se, this one, you cannot put it, but then you have to find a way of stopping the loop. Because this is what tells you when to stop the loop. If you want to have an infinite loop, you can write something like this, by the way. This is perfectly valid syntax. Actually, just that. That was just going to freeze your program forever. But, okay, more useful, maybe that. That is an infinite loop. Of course, if you want to stop an infinite loop, you need a break statement at this point. So, yes, I could go ahead and switch this one to like if I is less than s, break. I could do this, and then I can just remove it from here, and this will work the same way. Actually, do I have to flip that around? Yeah, I have to flip that around now because I use break, so I have to flip the logic. So if I is greater than or equal to, like that. Oh shoot. Put that before the if I is greater than s. Okay, maybe it has to be like that. Why? Makes me want to think. Okay, I is equal to 0. If I is bigger than s. No, it should have been the way that I had it. Okay, maybe s minus 1 so we don't go out of bounds. But why is it getting a 0? I'm not sure. This should make a difference. What did I do here? C out vector, my vector, if I, which is increasing every time. Oh, maybe move this to the top. That way it matches the proper loop. But still, I don't know why I'm getting a 0. That's weird. Where are those zeros coming from? Oh, I see. So maybe basically it was printing the right values, but then it went out of bounds, and then they're just printing probably something out of bounds. But yeah. But anyways, if I is greater than s, let me get rid of that s minus 1 and make this cleaner. Yes, we can. Okay, so anyways, yeah. So you don't need to have the condition in there, but you should, because this is horrible code right here with the break. It's just nasty. So this is so much cleaner like that than using a break statement. But yes, but technically, there is no error. It's okay. It's just syntax stuff. I mean semantic stuff. So I'm gonna delete that because I don't want anybody to be using break statements. They're not good unless you really have a good valid reason. So anyways, back to the one that I was showing you. Let me go ahead and actually remove this section of the code out. So, of course, we saw how big this is. At least, well, technically we have 3 lines and now we have 2 lines. But more importantly, how simple this looks. Okay, so this is a range-based for loop, and there's a couple of parts to it, and they have names to them, and the names are in the documentation. So I'll read you what the names mean. This is called the range declaration, the first part of it, int k, and then the my vector part is called the range expression. So let me write that. And again, that's from the documentation. The syntax for a range-based for loop is writing the word for, opening up your parentheses, and then you got range declaration, colon. So this is a colon, not a semicolon. The other ones above were semicolons. These are colons. And then you got your range expression. And then you got your loop. So you can, of course, just put curly brackets like that, or technically if it's just one statement, it's also okay to just put it like that. So technically here, I could do this, you know, and I think that's okay. Doing this like this is confusing for people because you might accidentally write code here, and that is not in the loop. So if you're doing it this way, then you want to put the curly brackets. If it's a single line of code, then don't put the curly brackets, but put it on the same line. That is my personal opinion, though. So, judgment may vary. You know, curly brackets is a nice thing to do. So, anyways, okay. So, yeah. So we got the range declaration and range expression. So what does that really mean? Okay. So what you need to do for a range for a loop is a way that you just get every single thing as you're looping through. If it's behind it, doesn't need a semicolon at the end. You always need a semicolon. In fact, I don't have a semicolon here, but you always do, like that. So here, I'll put it in both ways. This is okay, and then this is okay. But you always need the semicolon. Semicolons are a way that you tell the compiler that that is where that statement ends. And it needs to know where it ends, otherwise it assumes that the next piece of code is part of that statement and it's going to get confused. So always have your semicolons. So yeah, both of these are going to be doing the same thing. Advantage being, in this one I can easily add code, whereas in this one I cannot add code inside the loop, because if I type in code here, it's not going to be in the loop. So yes. Anyways, so the way this works is it basically takes a list, in this case a vector, and then it extracts the first element and puts it in K. But actually here, I do believe the way that I have it written now, it's making a copy of it. So this K here is actually a copy of the first element here. So it copies this over to K, and then you can do whatever you want with K here. When it comes back to the top of the loop, it takes the next element in vector and copies it again into K, overriding the previous one. And then you can do anything. And so it does that until it goes to the entire number of elements inside of the vector. So that's pretty much it. That's pretty much how this works. Now, as I said, it is making a copy of things. And so copies are not necessarily the fastest things in the world because, well, you know, this is an integer, not a big deal. But if you were keeping some serious stuff in this vector that took a lot of space, then that's not necessarily the fastest thing that you want to access. So how can I make this a little bit faster? Well, instead of making a copy, and also this won't work if you're trying to modify the vector. This will work for printing it. Like this will print the vector technically twice because I got the both for loops in there. Let me compile and run. You can see it's printing it twice. Again, I got both for loops. Let me just get rid of one of them so you can see just the vector once. It's just printing it, right? But suppose that I wanted to add a number to each of those, like +1 each of my indices. I could use the old method here. Comment this guy out and then simply do my vector I plus equals 1. And so this is going to print the vector before and after twice. So basically print it twice. Here we have the before and we have the after. As you can see, the 20s became a 21, the 6 became a 6, and so on. Okay? So essentially, the old school loop works just fine for actually increasing your values. However, you're about to see how this is not really going to work out for the one that we have beneath there. Well, I do see we have a question. So will the loop with the see out my vector be faster since it doesn't copy? As I have it now, yes, it would be indeed, because here we're not making any copies. We're actually manipulating the vector itself. So right now it's faster, but don't despair. I'm about to show you how to make this just as fast as this. So don't just assume that, okay, this is faster, I'm just going to stick with it. No, don't worry about it. We're about to make this. We're about to fix this. So, but first, let me show you the problem as it is now. Suppose that before I mean, I could do this. I could do K plus 1 and then see out K, and you will see that I am actually increasing the size. Oh, plus equals 1, sorry. And you can see that, yes, I am going to get all my numbers that look like they increased by 1, but they didn't really, because if I call the vector again here, and like this loop down here, you're going to see that they're still the old values. as you can see. So that really didn't increase them. They just increased the local copy before we printed it. So increasing it doesn't work like that. What do we need to do? Well, think about this. This is kind of like pass by value, and what we really want is pass by reference. So what did we do in functions to make something pass by reference? We added the ampersand. That's all we gotta do here. Just put an ampersand in there. And now, let's go ahead and do the addition after the printing so that it gets printed on the next run. So first it's going to print the old values, increase them, but we won't see the increase. We'll see it the next time we print it. That way you can see that it actually updated the array itself, the vector itself. And voila, there you go. The vector has been increased here after doing the +1. So yeah, that's all you gotta. And now you're not making copies, you're making a reference. So now you should be about the same speed between these two. I'd say that at that point the compiler will take care of doing any optimization, so they're both about the same speed. So there is a risk though of doing this. I suppose it's a risk that we have here, but we don't think about it. Technically, with great power comes great responsibility, right? So now you have an access to modifying the vector, just like you do here. I mean, here you could do any modifications you want. You're just used to being able to have that power. I suppose the same situation lies here. You could modify the vector at this point, and it would permanently modify it. But suppose that you just wanted to have read-only access, but still maintain the fact that it's being passed by reference. So basically we're saying we want it to be fast, but we don't want to give the user an ability to, for some reason, accidentally write code like this and actually modify the vector. So this is kind of a very situational thing, but you can do this. You can have the word const in front of it, kind of similar to how you do constants. And then if you try to compile it, it'll actually complain that it's read-only. So it will not let you modify things. Now, I don't think we have actually ever seen a situation like this, so it might be worth mentioning. Again, this is more of 202, the little const part, but there's this sort of idea that even though we are writing our code, we sometimes want to limit what we can and can't do in our code to prevent errors from happening. So, for example, suppose that we're writing this really long code and we create some variables that we know we never need to modify ever again. We of course make a constant out of that, right? We already talked about constants early on in the class. But why make a constant when you can make a normal variable? Like, okay, why do I have to, when I use pi, why should I set that as constant? Why can't I just make it a variable and not just change it at all? Just keep it the same all the time. Yeah, because we sometimes forget and we make mistakes. And it's better to protect ourselves to not make mistakes by making it a const. And so the same idea here. This const basically limits you from modifying something that you maybe don't want to. And so you protect yourself by putting this here, and you would rather have an error happen in the compilation process than have an error sort of slip by into production code. And so that's kind of the reason between these sort of, they're not crutches per se, but sort of limitations on what you can and can't do in code to avoid actual errors. That's the real reasoning behind that. So there's that. So anyways, you don't need to do the const part for the test. That's what you're really after. But you should know it anyways. So, okay, we know that this works just fine. As I showed you before, this time it'll compile because I don't have the const in front of it. And so we can kind of get rid of this +1. We don't need it anymore. There is one more cool thing that you can do to make this even easier to work with. And that is the idea of auto. You can see this works the same way, but what is this keyword? You have never seen this keyword in your life, maybe, and that's okay. Autos are cool, but they're powerful and they're dangerous sometimes. So what is an auto? Okay, normally when you're creating a variable, So if I create a double, you know, I know it's a double because I'm gonna be storing decimals in it. So I have to know that ahead of time and create that so that it actually can store fractions, you know, decimals. If I mess up, I'm putting an integer here, I of course basically lose the accuracy, right? That -3 becomes essentially a -2 more 5 becomes essentially -3, right? It became 320 because we forgot to put an endpoint, but it's a 3. And there you go. Okay, so we have to know ahead of time what this is, and C++ language forces us to do that. Okay, it forces us to always give a data type before we declare a variable. We cannot just defer it and be like, yeah, we'll let you know later. No, we can't do that. We have to tell it. Some programming languages, such as Python, allow you to create a variable and change anytime you want from one data type to another. I could create an integer t here, and then I could store a string onto it. I could switch the type of variable and make it store something else. Like, it's just variables in Python, they're just variables. You just store the data. Internally, it figures out how that data is going to be stored. If it's an integer, a float, a double, a string, an object, blah, blah, blah. It doesn't matter. It knows. It just knows. There are pros and cons to that sort of concept of storing variables. The pro being, of course, it's very flexible and nice to not have to worry about declaring data types. The con is that the reason that we have to declare data types in C++ is because it makes the language a little bit more secure. And by secure, I'm not talking necessarily about being able to get hacked, but in the sense that there's less chance of weird bugs or unexpected behavior happening. Because if the program, if when you declare a variable, you define the type, it knows what it is and what kind of operations it can do to that data. So if you have a plus and they're integers, it knows that it's okay to add. If you have two strings, it knows it's okay to concatenate them. However, suppose you add a multiplication sign, so that's the asterisk. If it's numbers, that's okay, it will actually multiply them. But suppose you have two strings in there. What are two strings with an asterisk in between them do? Like, that makes no sense to programming, in the sense that unless you create that as some specific operation, which I actually do in 202 for fun. But yeah, so what does that mean? And you can't really check that until you get to that line and you actually see that in Python, because those variables could be numbers. You don't know what they are until you get to that actual line of code. Whereas in C++, because it's not interpreted by a compile language, you actually you want to check that at compile time to make sure you don't run into those errors. And you can only do that if you know what the data type is going to be. And so that's why the C++ developer said, we are going to make sure that we know the data type so that we can do all this checking beforehand. If you have a function call, that way we can compare the parameters of the data type of the parameters with of the actual parameters compared to the formal parameters and see that they match or that they can be coerced. So, long story short, you have to have a type. However, they did see that people really like the whole idea of not having to think about what type some data is, and so they did introduce what are known as autos, which, while they don't allow you to change the type of a variable, that is always going to be the case in C++, that you always have to have a data type defined when the variable is created, they do allow a little bit of sort of saving. I don't know if it's necessarily saving time or thinking, but I guess it helps a little bit. And that is the idea of auto. I can replace the data type here with the keyword, it's a reserved keyword in C++ 11 and on. Oh, it even said the C++ keyword. Did you see that? Yeah, hey, nice. And so what does that actually do? That variable is still a double. I guarantee you that it's a double. However, I'm not telling it it's a double, but it is. And that's because, remember, you can declare variables by doing something like int, int g, or you can also declare and initialize at the same time, right? So if you are both declaring and initializing, as I'm doing here, you can get away with putting this auto, because what's going to happen is this: when the code is compiled, it's going to look at what it's being initialized with, and it's going to deduce what the data type should be to store that kind of data. It's a little bit dangerous because like this will be stored as a double because there's no F in front of it. If you wanted to store it as a float, you would have to put an F in there. And if you want to store an integer, it would have to have no decimal to it. So it's a little bit dangerous because novice programmers may not really realize what the data type is, and other errors could ensue from that. But I mean, it works. And so now I have these autos which I can use, and I can handle this variable. I just have to remember that it's an integer. And how do I know that? Or in this case, it's a double. How do I know that? Because I have to see what it was initialized with. It doesn't work with a string. Let's give it a try. Well, I guess we already had the CRT part. Why do we have a random bracket there? And then, yeah, we should be fine. Okay, there you go. There's an example with a string. So yes, it will work. It will work with all the built-in data types and some custom data types as well, such as string, because string is technically not built in C++. But for all intents and purposes, it's always included, even if you don't include the string header file. But yeah, so yeah, it'll work. It's dangerous though, because yet again, the only way that I know this is a string is because I have to look at the initialization. So, you know, that's kind of the thing. So what are they really good for? Well, they're really good for range-based for loops because you don't really have to think. Sometimes custom data types can be really nasty and complicated. If you put auto, it's very clean in a range-based for loop because whatever the type is, we'll take it out from that. And then basically we got a way of handling in each individual element without really worrying about the data type. So while autos are cool to use here, you can impress somebody, they probably don't know what auto is, they're like, ooh, fancy. You can even lie to them and maybe they'll think that you can actually have variable data types in C++ when you can't. But maybe they'll see that because they'll be like, oh God, you didn't put a data type there, like OMG. But you know that that's not true. So anyways, this is the real cool use of them with range-based for loops. You can put an auto there and you can keep this sort of very pretty looking, I suppose, in that it's always for auto. If you want a reference with an ampersand. If not, no ampersand there. And then just some temporary variable. Actually, I is pretty popular for this. I didn't want to use I earlier because I didn't want to confuse you with the int I here. That's why I use k, but I is pretty popular there. And then just the name of the vector. But yeah, now we had a question. Is there a way in Python to give a variable a property that allows only, say, string to be stored in the variable? You know, it does sound like something useful, but I'm not 100% sure. You can cast in Python, so you could cast something into something else, but could you force it to be one data type? I don't know. That sounds like something we could Google. The thing is, they're mutable, so like they can always change to another data type. So what you really want to ask is, can you force it to become one thing? Yeah, my goal is we don't have so much time that we'll try to get some Python next week. Could you force it to be one? I don't know. I'll have to Google that. I want to say yes, but at the same time, I don't know. Maybe not. Who knows? Well, it's a real big question. That's a good question. I never heard about it. Thought about actually doing that. It's one of those things like, if you have the power, why take it away kind of thing. So, I don't know. Google. If Google tells us anything real fast. How to force ensure class attributes are specific type. No, that's not really what I want. I don't know. I'll have to get back to you on that, to be honest with you. But anyways, are vectors ever one-dimensional, or is there such a thing as a multi-dimensional vector? Ooh, I knew this would eventually come up. So, in theory, you can have a vector instead of other vectors. You can have an array of vectors. So you can have multi-dimensional stuff. Let's go ahead and try that out, actually. So this will be interesting. I haven't actually done this in quite a while, so this will be fun. Okay, so we can do that right here. Yeah, why not? Let's go ahead and do that. So let me move this a little bit so that I can see this better. I'm trying to code on the stream video so that I can make sure that I don't get out of the frame, because I code it from the normal monitor, I start coding outside the screen, and then you don't see anything. So anyways, let's just for now comment out the C out here so we don't see anything printed out. Okay, that's whatever. Here, this one. Okay, so let's try to make a 2D vector per se. So you're still gonna have your same syntax. Let me bring it down like that. Okay. Let's make it a car. We don't use cars often as I'd like. And so we're gonna call this just V. Actually, well, here's the thing. If we're gonna make it a 2D array, then I think the syntax for this is gonna be like this now. I think that's how it's gonna be. It's like Inception. Think about Inception. Yes, it will be a matrix basically. I think that'll do it. Let's try it. Yeah, okay, sweet, it worked. Perfect. So basically, we are creating a vector of vectors of cars. That's what it is. So if this was integers, so we're saying Inception style. We have a vector, and that vector is made up of other tiny vectors. And those tiny vectors, we have to tell it the type of those tiny vectors too, because remember, we have to always define our types. Those little tiny vectors are going to be little cars. And voila, this is basically what you do. So let's go ahead and push back to our vectors here. So let's go ahead and push back a vector into our vector. This is like Roger, like from that movie Airplane with the names. But let's go ahead and create a vector here of just cars, and then create that one, call it R, and then let's push back into it. So R dot push back A, B, and then C. And yes, it would be a matrix, but we're sticking to vectors for this. Okay, and so now we have a little vector here. We're gonna push it into the 2D level by doing V dot pushback of R. We're gonna push 2 copies of it. As you can see, this is not exactly ideal, which is why there are better ways of doing this, but we're sticking to vectors. Okay. Let's make one more vector here. We'll call this one Z. And then in Z, let's push out like a message like hello or something. So H, and then just copy and paste this a couple of times. Like this, hello. And then let's go ahead and push the entire Z vector into our other vector. So that is V dot pushback of Z. Okay, let's see if this compiles. It compiles. Okay, we're good. We're making progress. So next, we need to find a way of printing this, which is going to be interesting. We will need a nested for loop for this probably. So let's go ahead and take our, okay, we just run a new one. For auto, we'll call this inner vector. Seems like a meaningful name. Of V. And then there, for each, so we're saying for each inner vector, and then we're going to print out each element of that. So we can put another auto, or per se, individual elements of the inner vector. And then for each of those, just go ahead and see out that individual element, followed by an end line, and then maybe put an end line in between each of the inner vectors, like that. We're going to put it like a flat thing. Oof, that worked. Okay, I'm glad that worked. I was a little bit worried for a second. Let me scroll down a little bit since you cut off. I cut off the bottom. So yeah, okay. So let's let me go over just entirely of the entire thing that I did here, because this got a little complicated. So there are better ways of doing this, but we are committing to using vectors because that's really what I'm focusing on teaching you. So yeah, we're sticking to that. Okay. So the problem when somebody asks is, can you do multi-dimensional arrays essentially with vectors? The answer is yes, you can. Because you can keep anything you want in your vectors as long as it's the same type of what you're keeping. So the idea is simple. Let me draw it for you. We know our vectors can keep anything we want. So we're creating a big vector which essentially right now has 3 things in it. But what are those data types that we have in here? Well, they're vectors themselves. So you have vectors inside of other vectors. And these little tiny vectors are all character vectors. So they store characters, cars. Because we decided that. They could be in the integers, but thought I'd change for a while and stop seeing numbers. So these are all little tiny car vectors in here. What are those made up of? Well, those little vectors have individual elements themselves that are actual cars. But this whole thing is a vector of something. And that something is, of course, little vectors. So hopefully, and please let me know in the comments, does that make sense? Does this line of code make sense? Because that's the big important line. And if it doesn't, it's okay, but please let me know, because then I can try and explain it again. In fact, it would help if it's a little bit cleaner. Remember, if we just wanted to make a simple vector, like of cars, as we did here, we just put it in here, the data type. But in this case, the data type itself is this whole thing for this tier. So that's why we have vector inside of a vector like that. And that's why the syntax looks like that. If we wanted to make a 3D array, we could. We would just replace that car with something else that said vector, and then the type of whatever the thing is. If it's car, we say vector car. So we kind of wrap it around. And this would be like a little matryoshka doll, okay? That's kind of what we're doing here. That makes sense. Yeah, okay, yeah. Now, okay, good. So we got the part about declaring it. Now let's actually kind of see why it's printing the way that it's printing. That's a lot easier to explain, fortunately. So, all right, what do we got here? We got ourselves we've inserted basically one vector here, which was ABC. Then we inserted the same vector again, just because I thought I'd just insert more things. And then we create another car vector, we fill it up with stuff, and then we throw it in. So we have to kind of do that little 2-step processes. Make the second dimension vector first, fill it up with stuff, and then just throw it in. And then make another one. It's like a little factory. Fill up the little baby vector, and then put it inside. Fill up another baby vector, and put it inside. It's not ideal, but then again, this is kind of what you do, right? So anyway. Furthermore, once you go ahead and create all these little vectors, how do we actually print them out? Well, with a 2D array, in fact, what if we wanted to print this out using our old school 2D arrays? Would it work or would it not? Let's go ahead and try that. So how do you normally print out a 2D array? You have two regular for loops which tell you the sizes of them. So I is equal to 0, I is less than size, which what is our size going to be here? This is the outer one, so this is v dot size, semicolon, and then I plus plus, and then our inner one, which you can use another iterator, so j is equal to j is less than, and then the inner one is called, ooh, what is that going to be size for the inner ones? We will have to do v I dot size, yes, okay, like that. Because we're getting the size of the individual vectors in there, which are these. And then from there, now we can say cout v I and j. I think that's, we'll see if this works. I think it should work, but we shall find out, because here's the thing. This is how we would do the other normal rule. But oh, we got one extra parenthesis somewhere. I've never actually tried to print out a vector this way, so I'm not 100% sure if this will even work. What did it complain about? Oh, I forgot my my j++. You can put vectors inside of vectors as long as, well, there's probably some sort of RAM limitations, but I've never run into any issues like that. Again, this is more a proof of concept. I would not really want to do this sort of mess. What did I do here? Oh, yes, that's why. Okay, there we go. Let me clean up. All right, moment of truth. I don't know. Frankly, it's like 50-50 if this is gonna crash. Oh my gosh, it worked. Wow, I'm proud of myself here. Let me comment out the older ones. Can't believe that actually worked. Yep, it worked, guys. Like, wow. Okay, so yeah, you can use the old method using the square brackets, just like if it was a normal 2D array. You can use that same method. If you don't want to worry about the range-based for loops, you can use your square brackets like this. So in theory, for assignment 9 Battle Royale, if you want to use a vector instead of a normal array, feel free, since you've learned it now. But yes, don't feel bad. Everybody feels like that sometimes, where you're like, is this going to work? And then it works, and you're like, okay, I don't want to touch it because it might break, right? But, oh man, there's definitely better ways of, like yes, there's matrices and all these other methods that you can use to handle multi-dimensional data. But if we are sticking to vectors, since this is, again, this is a beginner's programming course anyways, and this is pretty already more advanced than you anyways probably pick up anyway in the beginner programming course. Yeah, if you want to use 2D vectors, then that is what you can do. And it will work with the old C++ array syntax. Of course, I would encourage you to use the method beneath, because that's what I have used before, and that makes me feel better about myself than using this. It just feels like this just feels weird. This just looks so much cleaner too. Like, this makes more sense. You're saying, okay, for each of the vectors inside of the big vector, go ahead and print each individual element, and then you print it. This just seems so much more readable for somebody who is new to coding than this might be. This has a lot of numbers and tiny stuff in it, little signs and symbols and whizzes. This is what you would see if you're watching Hollywood. They'd be like, yeah, this is code. This looks more clean and more readable, especially if you pick good variable names. These are so-so variable names for auto inner vector, for every individual element in the inner vector. You could read it like this. So for every inner vector in D, and then for every individual element in the inner vector, print out individual elements. That almost reads like English. This does not. So you can choose which one you want. But now I've shown you both. So you have the power of choosing what is more comfortable for you to work with. But both can achieve the same results, as long as you have the ampersand, of course. So you both can modify the data. So yeah, okay. I think that's where I will stop with vectors. I do want to kind of jump into a little bit of searching and sorting, but there's so much more. This is literally just touching like the cover of the iceberg thing. You know, there's just a little peak of the iceberg. Because if you look at that reference function or that I posted for vectors, there's so many other functions that you can do. There's the whole concept of iterators, which we won't even talk about. Size is useful. Is there any? Okay, maybe I'll show you one more. One more that's very powerful is the ability to erase things in the middle of your vector. Yeah, I'll show you that one, because that actually is pretty nice thing you can do, which you cannot do with an array unless you shift everything around. So that one actually has merit for me to show you. So let me go ahead and comment out some stuff here. So I can leave those loops running, it doesn't matter. But I'm going to comment this. Actually, here, I'll just return 0 early before I do any of that. Yeah, I'll show you that one. If not, I guess if we don't get a searching and the sorting today, we can tomorrow. So okay, cool. So now we don't get anything printed out, so this looks cleaner. The question is, can you see what I'm doing? Yes, you can. Okay. Oh, snap. Okay. So if we go ahead and print out the vector here, the first one that we had, let's print it out and see what's up in it. Let's say we want to remove one of these elements in the middle, okay? So how do we do that? And we, of course, want to do that before, or here, we'll print the before and after. So let me just copy and paste this twice. I guess just so you can see the different syntax usage, we'll make that one be like that. Why not? So let's go ahead and remove. So I think there's a finite erase, but first let me just show you erase. There's also empty. There's so many things that I could go over, but let me show you erase. So let me paste the link here. So that's the one that has an example of how to use erase. And that literally came from the other link that I sent you. If you click on any of the functions, they each have their individual pages that you can read with very nice examples. So yeah, in fact, yeah, okay. So if you don't ever remember how to use a function, that's just the best thing you can do. So the way you erase is, oh, that's cool. Now I feel like you guys are gonna think a copy from this. In the example, they use the word my vector as their actual example variable, and I have my vector here too. But no, even though they came up with it first, I didn't look at that. But yes, now we have my vector here. I like using my variable names because then you see different examples for different variables. But I guess my vector was pretty not original, so there we go. Okay, so this is going to literally look the same way as it's there, I suppose, because of that. So what you want to do is you want to call erase. And so erase is a little bit interesting in how it works, because as you can see here, the function says it removes an element at a given position. Okay, so but the way this works with iterators, without trying to really get into how iterators work, is you need to call another function in here that tells you where the in fact, here, let me show you something real fast. Let's go ahead and just print out what this would actually return. And let's see if it even prints out anything. Because look, if I call this begin function, it says returns read write iterator, okay? I think that's gonna print an address, but let's see what that actually prints out. Ah, there's no overloaded thing that can actually even print that. Yeah, so that can't even print. So this is a special data type called an iterator, and it just tells you where the vector begins, okay? Let's just hand wave and say that. And so because of that, Because of that, to be able to erase something, you sort of need a starting point, and then you need how many items into the thing you want to erase. So suppose you want to erase, let's just say the first element, okay? So you could do +0. In fact, we're going to put a +0 intentionally here, just to make that easy change later. And then let's go ahead and call this and see what happens. Where is the issue? Line 31. Oh, here we go. Semicolon. That's the problem when you code in Python, you forget about semicolons and you just kind of, yeah. All right. Let's add a line feed between both of these so it's easier to see. Okay. So as you can see here, we had 20 in the beginning and now we don't. So if you call my arrays on begin, it erases the first element. Now, if you want to erase the nth element, you just have to add to it. That's why I put a +0 here. All I'm going to do is I'm going to change the +0 to be whatever I want. So if I want to delete the second element, then I'm going to do 1 here. Now, why 1 and not 2 even though it's the second element? Remember the whole indexing stuff. Start arrays, counting and everything starts from 0. So 0 is technically the first element and 1 is the second element. The example with the parking garage. So that's why now if I have a 1 there, it's actually going to delete the second element, which is the first 5 that we see. As you can see, here's 20, there's a 5, and there's a 0. Now there's 20 and 0. What do we want to delete? The 3. Well, what is that? This is 0, 1, 2, 3, 4. It's a 5. So we have a +5 here. Not +52. There you go. We deleted the 3. And that's it. If you check size and all these other things, they'll actually have the updated size, which is now 7. So all the other things get updated. So all you really have to worry about is how to insert and delete. So there you go. I think that's where I'll really stop with vectors now. Now you have a power of deleting in the middle of it. Very, very cool thing that you can do and very powerful. There is another delete function. I can't remember what the name of it is, other than erase. Insert, I don't know. And there are ways to enter in the middle to overwrite or just like flat out insert. But like I said, that's a little bit beyond the scope of the course. So I'll leave it at that. Feel free to use vectors in your assignments instead of arrays. But I am warning you, when you get a 202 on future classes, ask your instructor first if he's okay with using vectors. Some instructors are not okay with using vectors. For example, I wouldn't be okay with using vectors in 202 if I'm trying to show you how to use dynamically allocated arrays. But if the assignment is unrelated to that, then I'd be okay with it. And data structures, I let people use vectors all the time, unless I specifically say you want to code things in vectors and linked lists or something like that. So yes. Why won't erase 5 work? I believe it has to do with the way that the function is built. It requires an iterator, and so basically that is some sort of memory location. I don't think that you can do. I mean, we can try it. Last time I checked, this wouldn't just work. But let's give it a shot. Yeah, no, it complains. It's just the way that vectors work. I think there's a way. I mean, you could overload your own function once you learn function overloading to maybe get around that. But and maybe that's what the other erase function is that I know that exists somewhere. But at least for this kind of function, you need to have this iterator here. So it's just what you have to do. So yes, okay. So that's a lot of stuff that we actually kind of learned. This is starting to look like actual code, not just baby code. So that's kind of cool too. Let me go ahead and save this and kind of start out clean. Let's go ahead and do some searching, because sorting is not going to happen in 10 minutes. Do we have to start at the beginning? No, you don't actually. There are ways you can actually work your way from the end and so on. Do iterators recalculate each time during for loops as well? So iterators, you can think of that as a storing the spot in an address. And so, I have seen an issue where you run into problems like, okay, so I saw an issue back in, I think it was in 202 or 302, where people were using the erase function and it was messing up their for loops because of it. So iterators themselves, you can just think of that as pointing to the spot in memory where the element is. And so if you go to the next spot in memory, it's going to be whatever the next spot is at the time that the call is made to move to the next spot. So if you delete things in between, that's okay. It'll get to the next valid thing. But so that you don't have to worry about. What you have to worry about is begin will always point to the beginning. So if you're saying begin +2, but you deleted something that was like a +1, then the next thing you really want to look at is +1 again. Because if you try to look to +2, you would skip an element. So begin and your iterators will always point to the right stuff. But your math could be off if you delete things in the middle. So that's the only risk that you could run into. But if you're not deleting anything, then everything will work fine. So yes, there's more to the monster than I have spoken. But yeah, that's very situational. By the way, I did put a new book for the class that's what we're going to be using from now on. It's free, so you guys can check it out. It's on Discord, so that you don't have to pay $100 for a book anymore. Okay, so anyways, I'm going to give you a brief introduction into searching, and I guess we could actually use vectors for that. Why not? Because we've been talking about it for 2 hours almost. Might as well use them. That's if you want to make your own custom namespace. Don't ignore what just happened there. Okay. By the way, if you are indeed submitting the extra credit, please make sure you tell me who you are. Or otherwise, some people I have no idea. And even if you told me in the past, send me a reminder, because otherwise I have to like track you down. So please do on Discord. Okay, so we will probably not get to the ending of this, but that's okay. We will just pick up where we finished today. So, okay. There are two very useful things to learn when you're dealing with lists of data. And those are, one of them is looking through the data to find something. So the ability to search through any form of data structure is a very, very, very important thing for most of them. Some of them, maybe not that necessary, but I'd say like 90% of them. Like maybe for heaps, it's kind of pointless to search for things. But yeah. So it's a nice thing to learn because when you think about algorithms, and I have been talking about algorithms a little bit earlier, you haven't really seen a real algorithm. And so one of the most baby examples, and by baby I mean like easy examples of algorithms, are some of the most basic searching algorithms out there, or sorting algorithms. There are really complicated, not really, but there are somewhat complicated sorting algorithms out there. There's also easy ones. And while the complicated ones we will talk about once you take data structures, such as quicksort and so on, I can actually show you quicksort and mersort maybe. But you want to start out with an easy one, so you can kind of get the idea of coding a feature to do something that you want it to do. And so that brings us into the most basic thing. How can I search through an array and find something if it's found in the array or a vector? So first, I guess we gotta create something to search through. So let me just create a little vector here. Let's go back to integers now. I like integers. Let's call this list, although I hope that's not a reserved word. Okay, let's make it uppercase list. Yeah, I feel like that might conflict with something somewhere internally. So yeah, we'll make that, actually here,
to save space and lives, we'll call it just L. Okay? Vector list. We're calling a vector of integers called L, which stands for list. Okay? Now let's go ahead and insert things into that. So let's actually include stdlib.h, include time.h, so we can use rand. So we can insert random things into our little array. So because otherwise there's no fun in if we spoil if something is found or not. So let's just try to randomize it. So srand time.null? No, time null like this, yeah. So that seats our randomizer. And then we can generate random numbers by doing t or n for number equals rand mod, let's just say 20. Let's try that. Let's make sure I remember how to use rand. You see that generates a random number. There we go. And then if we run it again, different number. Okay, cool. Perfect. Good. Would have been sad if I live stream and forgot that. But hey, I did it. Okay, so we're good. Catastrophe averted. Okay, now let's make a little for loop that runs maybe 10 times. We have 50-50 chance basically. I think that's the math behind that. I++. So what am I doing? I'm tired. I equals 0, I is less than 10, I++. Okay. And so in there, we are going to go ahead and throw into our vector rand mod 20. So this should generate randomly a number range from 0 to 19, not including 20, but the range of it's a range of 20 numbers which are 0 to 19. If you count from that, that's 20 numbers. 20 would be 21 numbers technically, because again we start counting from 0. And so in theory, because there's 10 numbers that we're putting in, but there's a range of 20 numbers, I guess we have like a 50-50 chance of finding a number in there, okay? Let's just for now print out what we just created, the monster domain name. So auto ampersand I colon L. Interesting look. See out I. Actually, we don't need to modify it, so let's be proper programmers. And maybe instead, can we do this? Actually, I think this will complain. We'll see. So, like that. Okay? Let's see if we're good with that. Yeah, see, it complains when you do when you use const here. So, no const if you're using this like that, I suppose. Oh, it's still complaining. I still forbids declaration of I with no type. I don't know. Oh, maybe the whole reason why this was complaining was because I forgot to put the std equals c++ 11 at the end. So, anyways, okay. So, run this, and we have a list of random numbers. Okay, so make a guess. I'm gonna run it again. Think of a number between 0 and 20 and 19, and just think of it to yourself. I'm thinking of a number right now, and I'm gonna run it again, and let's see if we win the lottery or not. In my case, I got it. I was thinking of 10, and there it is. What about you guys? Were you thinking of a number, and was it there or not? Is it your lucky day or not? Yeah, let's do it one more time. I'll think of a number. All right, I thought of a number, and bam. This time I was wrong, because I was thinking of 8, and I got no 8. That's actually cool. We got a bunch of big numbers this time. Almost all in the double digits. So hey, one time I got it right, one time I got it wrong. That actually fits statistics correctly in the sense that we got a 50-50 chance. Oh, 13, twice. Hey, there you go. You're lucky. But you want to push your luck for one more time. Statistics are against you right now. They're saying you got very low chance of guessing the number. But then again, luck plays into it. So now I'm thinking of a number. I thought of a number. Think of your number. And here we go. Hey, I got it. Mine was 5, and there it is. Actually, it's almost in the same spot where my first guess was. Where's my first guess? Yeah, 10. So that's kind of cool. That's another part of the random part. So, question is, was your 13 here? It was. Ooh, that's pretty lucky. So, anyways, enough fun for there since we got 5 minutes. The question is, what if we want to do this manual guessing by actually automating it? So, like, if I was to guess a number here, then I gotta actually look for it visually. Can I search for the number after the randomization is made and see if the number that I am looking for is there? And the answer is yes, you can. It's very easy to do what is known as linear search. For linear search, all you gotta do is you got yourself a little for loop, whether it's the first kind or the second kind, doesn't matter. What you wanna do is you wanna compare what you're looking for with the current element. If it's found, then you just return true, return the index, whatever you want. Success message. If it's not found, you keep going until to the next element, and you do the same thing again. And you keep doing this until either you find the item you're looking for, or you reach the end of the list, at which point you say, I'm sorry, it was not found, you didn't guess right. So, let's say that the number we're guessing for, actually, let's make it interactive. We'll store it in a variable that we enter from the user. Int guess. We'll set it to 0 initially, and we'll say cn guess. We are gonna run out of time. That's okay. Okay, and then here in our guess, I guess we'll speed up and then I'll go over it again next time. So we're gonna say if statement guess equal to I, simply cout found it at index. Actually, we can't even print out the index because we're using this method, so I just found it. And then I suppose let's make a boolean called found. Yeah, this will work better so that we can have the messages work out correctly. We'll initially set it to false, saying we haven't found it. If the guess is equal to I, then we'll actually just set the boolean to found. Found gets true. Okay, that means we found it. That way, after the loop, we can check if found. We can see out found it. Otherwise, we can say better luck next time. Yeah. The reason I'm doing it like with the boolean is because if I do it in here with the if I do it how I had it originally, I can't have an else clause here because you've still got numbers to look for. So the only way that I can figure this out is after I'm done looking. So that's why I'd rather just set the boolean to true here and do it outside so that I can have my else clause work nicely. So I'll talk more about that next time. But let me just show you that this runs. Let's put that 13. Oh, this spoils it because we see the numbers first. But okay, that's okay because we can see if it works. 9 is there, so this should find it. It does. Let's run it again. Let's put a number that is not there. So 10 is not there. So we put 10 in. Better luck next time. So we can see actually that actually worked out because we can see it working. So for example, 8. 8 is there, so it finds it. Let's try 8 again. It found it. Let's try 8 again. This time, oh my God, it's everywhere. Yeah. 8 again. This time it's not there. That was a lot of 8s in a row. So as you can see, it works. Although next time what I'm going to do is I am going to flip around this part to after so that we can make a guess before we see the solutions. So then we can actually have a proper, exciting game of gambling. Yes. Yeah, so what we just want to move is the printing part. Let's move the printing part after. So basically, this one right here, move it to the end, like that. Enter the guess. There we go. Oh, that's not just random there. So let's try a 6. Better luck next time. There we go. Let's try it again. Let's try a 4. Better luck next time. Damn. Okay, come on. 3. Found it. There we go. So as you can see, it shows you the list after so that you can see that there's no shady stuff happening. But yeah, that's pretty much it for the day. So we'll go over that example tomorrow because we did kind of go quickly, and I do want to spend some time actually more talking about that. But that is what is known as linear search, and it's very straightforward, but it's not that fast. So we will talk about ways to make searching faster next time. Maybe throw in some binary search in there. So how do we turn the index if we found it? If you wanted to get the index back, the best solution for that would be just to use the other kind of for loop. I'll show it next time. But anyways, I thank you all for being here. I hope you guys have a wonderful day. I'll see you guys tomorrow at 9. Thanks for hanging out. Hope you learned a lot today. Vectors are cool. So I think you actually learned something today that is really, really useful. So, I mean, not that you don't learn useful stuff other than this, but at least today you've learned something that you would probably will use forever if you're coding in C++. Vectors are pretty useful. So, I'll see you guys tomorrow. Stay safe. Take care. Bye.